So the magnitudes of formation constants are influenced by a number of effects, and one of which is the nature of the ligand. Others that you'll kind of commonly see are going to be the oxidation number on the actual transition metal. And then there's, of course, a lot of other electronic structure related factors, which you'll see throughout this chapter. But let's start off with a couple of examples that are illustrating the ligand influence on this process. So let's think about two reactions. So the first one now is a tetra-agua complex of silver 1. And then just assume it's gonna react with 4 ligands. I'll mention what they are in a moment. To really effectively make the new ligand complex, but then of course expelling 4 waters in the process. And then let's consider the same type of reaction, except now we're going to use copper 2 plus. So the differences are in these two cases is obviously silver and copper are in the same group. Copper's at the top of the periodic table, silver's in the middle, of course. And the copper is 2 plus charged, which basically means it's a D9 or 3D9 metal center. Copper is 1 plus charge, so that effectively renders it as a D10 species. And there's a bunch of other things too. Silver is going to be tetrahedral. Copper is pseudo-octahedral. So we'll get into this in a little bit. But let's just consider those reactions and let's kind of figure out what happens with the formation constants that are measured at room temperature if you change the nature of the ligands and see the influence of that ligand binding to silver 1 plus and copper 2 plus. So here is a summary of this, and this is just right out of your textbook. But what I want you to recognize is that if you kind of look at the first ligand, which is going to be NH3, NH3 seems to have a much greater affinity for copper 2 plus. So it's basically got a formation constant of 17,000 as opposed to 2,000. And then if you now go over to the halogens, and remember fluorine is the most electronegative element, it's on the top right. It's also considered a very hard base, but we did not really talk about hard soft acid base concepts yet. I was going to bring this up in a future chapter. But anyway, the concept there is notice that copper 2 has more of an affinity for fluoride ion than silver has for it. But then if you now go down the periodic table and you make this change to chloride, you'll notice that everything now changes around. Now suddenly silver makes a more stable compound with respect to copper when chloride's involved. And then if you make the L equal to bromide, it gets even more exaggerated. Now the formation constant for the silver compound is basically, if you just kind of consider the fact that copper is 1 and the silver is 20,000, it's basically a 4 order of magnitude more favored interaction with silver with respect to copper. And that tells you that there's this complicated factor of the nature of the ligand seems to really matter here. And it's not just the charge on the ligand, and it's not simply things that you would nominally think are going to be straightforward ideas. And it's going to really, in the end, be how these ligands sort of interact with these transition metal centers in different coordination geometries and in different manners as a result of effectively how they're bonding specifically with the transition metal and the types of bonding interactions they can impart. So as I said, a lot of these values can be rationalized using hard soft acid base concepts from developed by Ralph Pearson, but we will bring that up in a future discussion. So what's the final thermodynamic effect that we really consider to be very important in inorganic coordination compound formation? And this has to do with the Chelate effect, which we discussed a little bit when we talked about nomenclature and some of the structures of the typical coordination compounds back in chapter 9. But just remember now, the chelate effect is an entropy-driven process, so it's going to show you that delta S actually has a big influence on the actual net resulting equilibrium constant. And that's kind of an unusual thing because most reactions in chemistry are really driven by enthalpy. So they're really enthalpically driven and not entropically driven. But the chelate effect is largely an entropy-driven process. So what is that? So if we just use a couple of examples here, what you can kind of do is, in the first case here, we're gonna talk about this cadmium complex. So what you're doing in this particular case is that you're going to replace 4 of the waters with 4 methylamines. And you then look at the thermodynamic parameters that are associated with that process. And you'll notice that delta H is negative, but so is delta S. So that's indicating that this reaction is basically being driven primarily by enthalpy. Because obviously if the sign of delta S is negative, that effectively makes the minus T delta S a positive T delta S, and that actually is making delta G more positive. But the reaction is still favored, and the equilibrium constant for that is 3 times 10 to the 6. Now let's change it. So if you remember what ethylene diamine looks like, so if you remember, this is one of the classic chelates that we're going to use here. And that when it binds to a metal center, you basically can kind of make a 1, 2, 3, 4, 5 membered ring by doing that chemistry. And the 5-membered ring imparts a lot of stability to the actual complex itself. But what I want you to notice is that now, instead of using methylamine, if you use ethylene diamine to displace the same 4 waters to make this complex, you see that the delta H value is very similar to what you started with in terms of the cadmium methylamine complex. But the key difference is, look at what happens to the delta S term. That now is positive. So that basically is making the minus T delta S term more negative, and then that's actually making delta G more negative. And that's the net result. And the more negative delta G is, the higher the equilibrium constant. And then this particular case, the equilibrium constant went up 4 orders of magnitude. So what is like driving that? Well, there's 2 things that actually happen when you think about what is actually going on there. Part of which is that you are still displacing 4 waters. But the stoichiometry of the reaction is basically you're installing 2 ethylene diamines. So that increases the entropy in the universe because you have more moles of products with respect to reactants. And that is the main driver of this. But there's another thing that goes along with it, is recognize the fact that once this thing chelates, if you wanted to break one of these metal-ligand bonds, this entire structure will not fall apart. In fact, it's poised to come back and bind back to the metal. And that basically means that its formation constant is going to necessarily be higher because it really can't escape into the free solution. It's hanging on because of the fact that you have this chelate effect. And then the same thing happens for copper. So if you add, for example, 2 amine ligands to make the, basically the diamine complex, again, very much not an entropy-driven process because the entropy value is negative, but the overall reaction is still favored, and it has an equilibrium constant that's 10 to the 7th. So now, instead of using 2 amine ligands, just use 1 ethylene diamine to make them the mono ethylene diamine compound, and then you'll see that the thermodynamics of this in terms of enthalpy is about the same. But the big difference now is that the entropy term is now plus 23, and that then drives the delta G value to more negative values, and then that increases this equilibrium constant, again, by about 3 orders of magnitude with respect to using 2 monodentate ligands. So that is the chelate effect, in essence, is this entropically driven process that then gives you much higher formation constants or much higher stability constants for the final products that are produced. So you're making the product formation more favorable by putting entropy on your side. And remember, this is exclusively driven by the fact that if you took any of these reactions and write them out as reactants and products, you're going to have more moles of products as a result of the chelate effect. And that is, in essence, what drives the whole process. So here's another interesting illustration of the same process. What I want you to see, again, is if you put one EN on, and then you put two ENs on, and then you try to put the third one, that's basically what you're doing here. And what this is telling you is, again, you have copper 2, so that's D9, and then you have nickel 2, which is D8. And the thing that I want you to kind of focus on is notice the first one goes on with an incredibly high formation constant. Then the second formation constant's a little lower, but then the shocker in this one is the third one is incredibly small. So that's really telling you that copper 2 does not want to have 3 ethylene diamines attached to it. And that is going to be the basis for lots of things we discuss later. But one of the reasons that occurs is a result of what's known as the Untitled Effect, which we will talk about later in the chapter. But then if you see what happens with nickel, where you have effectively a D8 transition metal complex, the first ligand goes on, and that's just showing you, K1 is high, K2 is a little less, K3 is definitely lower, but it's not being attenuated like it was in the copper 2 case. So you're kind of seeing here that now you have two transition metals, same charge, same starting material. They're both the agua complexes, and they're right next to each other in the periodic table. But one is a D8 configuration, the other is a D9, and that seems to have a massive influence on the resulting process of going from the K2 to the K3 equilibrium. And that, again, is going to get explained in a lot more detail later on in the chapter. But I want you to recognize that electronic structure is influencing the chemistry. And that will conclude my brief introduction to metal-ligand bonding thermodynamics. Thank you.